Hello everyone, I am Rekha over here, assistant professor from JSS Engineering College, Bangalore. So I am from Department of ISC, JSS ATE Bangalore. So today I am going to explain you about the module 3 of data processing circuits. So this module basically consists of combinational circuits wherein we need to send the information over the many applications. So these circuits helps in many huge applications. So let us discuss what exactly is this application circuits and what are these combination circuits we are going to design, discuss and then analyze these operations. So let me start here with the major outcomes of data processing circuits. So before I explain what is the outcome, so let me talk about data processing circuit. What is data? So data could be your information moving, so in a communication line. So information can be in the form of text, voice, video or any signals that can be sent. So how exactly this data will be processed? So to do this processing we require a major designing of the circuits. So let us discuss about the data processing circuits. So the outcome of this lecture is you will be able to design multiplexes as well as demultiplexes, and then you will be able to understand the concept of decoders, encoders, and you will be designing varieties of encoders and decoders, and you will be knowing about the purpose of parity checking and as well as generating. So you can also design comparator circuits. So you will be understanding the concept of memories like PLAs and PAL. Finally, we will be writing an hardware description language for all of these data processing circuits. So let me start with multiplexer. So multiplexer is once again a combinational circuit, so which is a device that allows digital information from many resources to be routed onto a single line for transmission. So it is a device, it is also called as MUX, so which carries many informations, and out of this many informations one output will be redirected. So this input lines we call it as data input lines, and one it has got single output line. This data input lines are selected out of many inputs. Only one input is selected and redirected at the output. So this selection of the inputs, we have an additional inputs called as selection inputs or control inputs. It is also called as selection signals, control signals. So let me discuss about this block diagram of multiplexer. So I will start with multiplexer operation. So multiplexer block diagram is written this way. We have inputs and we have an output. As I said in the definition, we have multiple inputs. The inputs are designated as I0, I1, in general IN, and output is designated as Y. So this we call as MUX. So my question over here is, these are many inputs and single output. So out of this many, which one will be selected at the output side? So let us think or decide which one has to be selected at the output side. So these are based on selection inputs, are also called as control signals. Let me take up an example. So I will consider MUX with 2 inputs and 1 output. So I will define this as 2:1 MUX. So how many selection lines over here? This selection lines is calculated by taking this number of inputs. So now the number of inputs are 4. In this case it is 2. So in this case it is 2. So what should be my n value to get this 2? So n should be 1 to get this 2. So if n is 1 means number of selection lines will be 1. So I write here 1 selection line. The selection line is represented by S0. So now my S0 can be 0 or 1. If my S0 is 0, this is my input. I have 2 inputs, I0, I1. So I have 2 inputs, I have 1 selection line. So the selection line can be either 0 or 1. So right. So here if my selection line is 1, then I0 will be directed at the output side. So my output will be here now, it's I0. If in case my selection line is 1, then the input is I1. So that input I1 will be selected at the output side. So this is a truth table. We call this as truth table of 2:1 multiplexer. So finally 2:1 multiplexer has got 2 inputs, 1 output and 1 selection line. So how to select this input? So it's based on the selection line. So now let us take an example of 4:1 mux. So suppose we have 4 lines. So we have 4 lines. We designate this as I1, I2, I3. So we have 4 lines, we know this, and we have 1 output Y. So my next selection lines. So now I am going to decide selection lines. How many selection lines do I require for 4:1 mux? So for 4:1 mux, once again I will take this formula. So where number of inputs now 4. So n represents 2. So 2 square becomes 4. So my selection lines will be 2 bits. So now in 4:1 mux I will be having 2 selection lines. So 2 selection lines are designated as S0, S1, where S0 is LSB and S1 is called as most significant bit. So S0 is called as least significant bit, S1 is called as most significant bit. So now based on this we are going to decide which inputs has to be directed or selected to the output side. So now we write a truth table for 4:1 mux. So how do I write truth table for 4:1 mux? So once again the same truth table I am going to modify. Instead of only S0 in the previous case, now I am going to take 2 bits, that is S0 and S1, because I have already designed for 4 inputs, it will be 2 selection bits. So 2 selection bits. Now I am going to write, if we have 2 selection bits, I am going to generate 4 combinations. How much I am going to generate? If there are 2 inputs, selection bits, so out of 2 I can generate 4 combinations. So 4 combinations is written like this: 0 0, since this is LSB, this is MSB, so I write like this: 0 0, 0 1, 1 0, 1 1. So these are the 4 combinations that is I am going to write for selection bits. So now what will be my output? I have got 4 inputs. Out of this 4 inputs, I am going to select 1 at a time. That is what multiplexer does. So multiplexer is a device which has got many inputs and single output. So out of this many inputs, the major over here selection. The selection is dependent on the bits what you are going to apply here. If I am going to apply 0 0, then I naught is directed. If I am going to apply 0 1, then I1 is directed. So I am applying 1 0, then I2 will be your output. Similarly 1 1, I3 will be your output. This is how the multiplexer works. So similarly we can design many multiplexers. So now this is what I have just now explained, 4:1 mux. So this represents the block diagram. You can just see over here, 4 inputs, 1 output, 2 selection inputs. So in this we have designated this input as I0, I1, I2 and I3, and we have an output, 2 selection lines. So this selection lines, once again we are going to generate based on this. So finally there is an additional input, this is called as enable, which I can make this multiplexer anytime enable or disable. So this enable is designated as G. If G is 1, your multiplexer is enabled. If G is 0, your multiplexer is disabled. So this is an additional input wherein you will get anytime I can enable or I can disable this IC. You can just closely check this selection lines, I0 0 0, I0 0 1, I1 0 2, I3. So finally putting all together, I can write the above information can be written in the form of Boolean equation. So the Boolean equation output Y is given by your I0, and you have got 2 bits with this I0, that is 0 represents complement, S0 bar and S1 bar. So I0, S0 bar, S1 bar, plus we have I1 with S0 bar, S1. So similarly we write this equation. So this is basically a SOP equation. You will get sum of products. So this is a Boolean equation. So you can write on the same equation, the logic circuit has been written. So what I explained previously was a block diagram. Now what I am going to explain here is the internal architecture, or I can tell internal circuit of 4:1 mux. So till now you are watching only block diagram. We add 4 inputs, 1 output, 2 selection line. What is there inside this block? So inside this block consists of gates. So these gates are designed based on this equation. So we have 4 terms here. So we have 4 AND gates and we have OR gate. So and also dot represents NOT gate. So we have AND gate, OR gate, NOT gate, and selection lines are connected to each gates, and input lines are connected to single AND gates. So based on, suppose I take S0, S1 as 0 0. So if these 2 terminals are 0, so 0 represents, there is an inverter here, represents 1 over here, and there is a one more odd NOT gate here that represents 1. If my I0 is coming over here, so all the inputs of my AND gate, first AND gate is 1. If the inputs of AND gate are all 1, my output will be 1. So out of this 4, this input will come to the OR gate. So OR gate will be selecting out of all 4 1. Since I am sending S0, S1 0 0, so this gate will be high. The rest all other gates are low. My output of this gate is low. Output of this third gate is low. Output of fourth gate is low. So only the output of first gate will be high. So my output over here is I0. It is nothing but I0. So nowhere I1 is coming into picture. I2 is not coming over here. I3 is not coming over here. So whenever I apply S1 is not 0 0, only my output will be I naught. Similarly, I can redirect these inputs to the output side. So, based on this selection line. So, similarly, if I take 1 0, so S naught will be 1 and S1 will be 0. So, in this case, if this is 1, my this AND gate is high. So, S naught is 1, this AND gate will be high. So, based on this, we are going to decide which one has to be directed to the output side. So, at a time, one of the AND gate output will be high, the rest of the output of the AND gate will be low. So, finally, my input to OR gate is only 1 and 0 0. So, based on the output of AND gate. So, this is the logic circuit of 4:1 mux. So, similarly, I can generate 16:1 mux, 8:1 mux. We have got types of multiplexers. We have got 8:1 mux. So, let us discuss types of multiplexers. Multiplexers is also termed as mux. So, we have 2:1 mux, we have 4:1 mux, we have 8:1 mux, 16:1 mux, 32:1 mux. So, there are more number of multiplexers available in the market. So, in the form of IC. So, we call it's a medium scale integrated chip. So, we have MSI, medium scale integration IC, which are available in the market. So, we have all this option, no need of connecting all those gates. So, everything is available inside the IC, only thing you need to give the inputs, selection inputs and take the outputs. No need of connecting AND gates. So, now let us once again brief the types of mux, how many inputs, how many selection lines and how many output. So, first 2:1 mux. So, 2:1 mux, how many inputs are there? Yes, how many inputs? 2 inputs, right. So, we have 2 inputs. So, how many selection inputs? 1, yes. 2:1 mux, 2 inputs, 1 selection input. Coming to output side, always my mux has got only 1 output, right. Now, we will discuss about 4:1. So, when I talk about 4:1 mux, so how many inputs will be there? Let me know the answer from you. Yes, how many inputs in 4:1 mux? Right, it is 4 inputs. And how many selection line? Yes, 2 selection line. And how many output? Of course, we will have only single output for multiplexer. So, coming to 8:1 mux. So, how many inputs? Right, 8 inputs, 3 selection lines, 1 output, right. Coming to 16 inputs, 4 selection and 1 output, 32 input, then how many? 5 and 1. So, this is how we are going to see different combinations of multiplexers available. So, similarly, we have a logic circuit for all these combinations. So, we have AND OR circuit. So, in the market, no need of you connecting the circuits, many circuits. For example, if you take 16:1 mux, so many AND gates, so many NOT gates, right. So, better we are going to design the circuits using IC. So, let us discuss what exactly, what are the applications of mux. Applications. So, majorly it is used in communication field. Right. So, networks, when I talk about communication, its networks field. So whenever there are multiple sources coming into the same, I can take up multiple connections coming onto the same channel, then I can select one at a time and can redirect to the output side. So these are the applications. Then I will be talking about advantages. Less cost. So why it is less cost? Because instead of building different circuits for multiple sources, each circuit, it is tedious to build that huge circuit. Instead, I can redirect all this multiple resources onto a single line, whenever required, then only I can send or redirect this to the output based on selections. So less cost, right? And then complexity will be reduced. So these are the advantages. So now let us start building. I'll take up an example of one application. So I can implement Boolean function using multiplexer. So we'll take up an example. You can just see the example over here. I've taken three variable input, wherein I have the min terms indicated as 1, 2, 6 and 7. So this is a function, through 3 input function. Now I am going to realize this function. Instead of using SOP circuit, I can develop this function using multiplexer. So 3 variables x, y, z. I have taken all 7 combinations. So 8 combinations. We have 0, 1, 2, 3, 4, 5, 6 and 7. So 0 to 7, it is 8 combinations. 2 power 3, you will have 8 combinations. And I have written the function, that is output over here, based on this min terms. So min term over here is 1, 2, 6 and 7. So wherever that particular 1 is there, you can see over here 0, 0, 1. I will be writing my output as logic 1. So min term. So once again coming over here, 0, 1, 0 represents 2. For 2, my output is logic 1. So for 6, 1, 1, 0, once again my output is logic 1. For 7, 1, 1, my output is logic 1. So 1, 2, 6, 7, 1, 2, 6 and 7 represents logic 1 according to this equation. The rest all I have made this as 0. So now I am using 4:1 mux to realize this expression. So how to connect this input and how will I get this output? So as I said, in 4:1 mux we have 4 inputs named as 0, 1, 2, 3 and we have 2 selection lines named as S0, S1. So coming over here, since I have got 2 selection lines, I will be using this 3 variable, right? So I will be making this 3 variable, I will reduce it to 2 variable. These 2 variables are x and y. So I will be giving these 2 x and y variable to S0, S1. So now my for mux selection lines will be x and y. So what about this third variable? I can't leave this third variable as it is. So you need to use this in my circuit. So how to make this third variable also work into the circuit? I eliminate this third variable by making this input for this function. So this acts as an input to the mux. So my input to the mux will be based on my third variable combinations. So my third variable, you can just see over here, I have divided this 8 combinations into 4 combinations. You can just see this horizontal line. So 0 0, since I am making x and y as selection line, you can just see over here 0 0 0 0 represents a single selection line. Since both are equal, 0 and 1, 0 and 1 both are equal, I can make this as a single single term. 1 0 1 0, I can make this as one combination, 1 1 as another combination. So out of this 8 combinations, I have made 4 combinations by taking into consideration 2 common variables. So you can just see over x and y, it's repeated over here 0 0 0 0. I'll take it as a single term, 0 and 0. Here 0 and 1, I'll take it as 0 and 1. So here 1 0 1 1. So finally my input, the selection line should be of 4 combinations. I have got 4 combinations out of this 8, that will be 0 0 0 1 1 0 1 1. So what about this third variable? This third variable I am going to generate, we call it as map entered variable. I am going to reduce this, I am going to give this as an input. So this will become an input to the mux. So how do I write this input? Whenever my function, I do this grouping like this, I have already reduced 8 to 4 like this. So this 2 grouping, always 0 and 1 at the output side represents Z. This is the law or a rule for MEV. Whenever it is 1 and 0, it will be, the function will be in terms of Z bar. This is a rule. Whenever both are logic 0, my output will be 0. If both are 1, my output will be 1. So my input to the mux will be in the function, right? This function represents 0 1 is represented as one of the variable. So that variable is nothing but Z I have taken here. So it is Z. If I take it as 1 and 0, so it will be Z bar, the function will be Z bar. If it is 0 0, it is logic 0. If it is 1 1, it is logic 1. So finally these 4 elements are connected to the input to the multiplexer. This 4 will become a input to the multiplexer. You can just see over here 0 0 represents the first input, I naught. So that I naught is nothing but I have given as Z. So 0 1 is I1, where I have changed this to the variable map entered variable. Now my map entered variable is Z bar. So I have connected here Z bar. So coming over here, 1 0 represents I2. In I2, what I will be connected for I2? It is logic 0. Similarly for 1 1, it is nothing but I3. I will be connecting logic 1 for here. So my output function f, whenever I give 0 0 0, means here 0 0, I will be giving, what will be my function output side? So if I give 0 0 and if my Z is 0 and if my Z is 1, then my output is redirected here. So my output will be Z. Similarly, if I go for second condition, when I apply 0 1 over here, so based on this Z, if Z is 0 or Z is 1, right, my output will be second. So that is nothing but Z bar. So based on this selection lines, if it is 0 0, Z is selected, 0 1, Z bar is selected, 1 0, 0 is selected, 1 1, 1 is selected. So based on this 4 combinations out of S0, S1, all this inputs Z, Z bar, 0, 1 will be selected to the output side. So this way I can implement 3 input function using 4:1 mux. So no need of connecting the circuit, writing a K-map, and then finally you are getting a pause or stop function. You will be drawing the logic circuit using AND and OR gates. So instead I can directly use a multiplexer IC to do this output. Similarly, I have taken an example over here, 4:1 mux. So you can just see how many inputs are there. 4 inputs A, B, C, D in the truth table. We have 4 inputs, and we have a min terms here, summation M 1, 3, 4, 13. For 8:1 mux, as we have discussed earlier, you require how many selection lines? 3 selection lines, and you require 8 inputs. So these inputs represents 0, 1, 2, 3, 4, 5, 6 and 7. So now these are the 3 selection lines. Alright, but coming over here, we have 4 input function. Since we have 4 input functions, it's a 4 variable, right? But for 8:1 mux, I require 3 variable. How to reduce this 4 variable to 3 variable? Once again, as we have discussed in the previous problem, so in this problem also, I am going to reduce this 4 variable to 3 variable so that I should fit this in 8:1 mux. Because for 8:1 mux, I require 3 variable, right? But we have 4 variable. So once again, we have to go eliminate this 4th variable. So how to eliminate? We use MEV technique, map entered variable technique, to reduce this. So how exactly is done? Once again, let us discuss. This function can be implemented using 8:1 mux. So how to write the truth table for this? Since we have 4 inputs, we will write 16 combinations, that is 0 to 15. So we write all these combinations. At the output side, we are going to write this terms. So these are called as min terms. So wherever these terms are there, right, this variable is there, then I am going to put mark 1 at the output side. So my output of the truth table is F, input is A, B, C and D with all 16 combinations. So my output is single output, which represents this function, this min terms. We call small m represents min terms, summation of min terms 1, 3, 4, 11, 12, 13, 14 and 15. So now we write here based on this. So wherever there is 1, that is 0, 0, 0, 1 represents 1. So I will write 1 over here. Next is 3. So 3 comes over here, 0, 0, 1, 1. So it will be 1. So coming here 4, 0, 1, 0, 0 represents 4. Likewise for 11 I have written here, this is 12, 13, 14, 15. So 1, 3, 4, 11, 12, 13, 14 are represented as logic 1 and this truth table. So the rest remaining variables are treated as zeros. Whichever are not mentioned in this function are treated as zeros. So now I am going to write all this, fill up all this 16 combinations. Now I am going to divide this 16 into 8. Why? Because I have 8:1 mux. So 8:1 mux, I require 3 selection lines. So for that I am going to choose A, B, C as selection lines. So for that I have divided now for 8:1, since I want 8 combinations. So I have divided this, partitioned like this, 16 has become 8 here. So now in this 8 combinations, you can just once again watch A, B, C. Since I am taking A, B, C as selection inputs, please do observe these 3 A, B, C terms, variables. Okay. So this A, B, C here 0, 0, 0 twice it is repeated, 0, 0, 1 once again it is repeated, 1, 0 repeated, 1, 0, 0 it's repeated. So likewise, so it is repeated 16 will become 8. I am going to consider this as a single term. Instead of 0 0 double twice, I can make it as a single 0 0. So that will be reduced to 8 bit. So I will show you this as an example. How to reduce the truth table. So how to reduce the truth table? Now we have 16 combinations. I am going to write this combinations. So if you can see, if we can divide this 8 combinations, 16 combinations into 8 by dividing like this. So we have twice repeated here, same thing is repeated here. So I'll eliminate, I write like this 0 0, this two together 0 0, then 0 1, 0 1 0, then 3 4 5 6 7. My truth table has been reduced from 16 combinations to 8 combinations. So now what I should do with the last variable, that is D. So this D, anyhow it is repeating 0 and 1, you can just see here 0 1 0 1 is repeated. So now I will take this D as a output, as a function of output. So I am going to write my output whatever I have generated in this example. So in this example my output is 0 1 0 1, right, then 1 0, then I have 1 0 0 1 0 1 0 1, right. So we have 0 1 0 1 1 0, then coming after that zeros, then I have 0 1, then I have 0 1, then I have 1 1. So based on this, now I will be writing my output as a function of this D. So if my output is 0 1, I represent this as D. So for this combination, the first combination, output is 0 1. So if it is 0 1, I will be writing in terms of D. So this was my output. So now once again 0 1, it represents, for 0 0 1 combination we have 0 1. So for that what I should write? Once again my output is D. So now this is 0 1, next is 1 0 I have. So for 0 1 0 combination, 0 1 0 combination, 1 0 represents D bar. Alright. So for 0 0, that is 0 1 1 combination, 0 0 represents logic 0. So similarly I will be writing for all these combinations. So next combinations, logic 0 1 0 0, then we have 1 0 1 option. So 1 0 option, it is 0 1. So for 1 1 0, it is 1 1, it is logic 1. For 1 1, it is once again my output is 1 1, so logic 1. So these will be treated as you have got 8 combination, 8 different combinations. So we give this as input to multiplexer. So of course we had 16, we have reduced it to 8 to give it to 8:1 mux. Since 8:1 mux as only 8 inputs. So now for that 8 inputs I am going to give this function. So in this last variable I have eliminated in terms of one of the input to the multiplexer. So this A, B, C is connected to selection lines and D will be connected as one of the input to the multiplexer. As it is, I can't connect. So what I am going to do? I am using a rule. This rule is called as map entered variable rule. So based on that rule, I will be connecting to the mux. So that rule specifies whenever there is 0, 1, it will be normal input. If it is 1, 0, it is complemented. If both are 0, 0, then it is logic 0. And if both are 1, 1, it should be logic 1. So now, how to connect this to the circuit? You can go to the circuit diagram over here. The circuit diagram, you can just see I have connected here S0, A, B, C, where C represent least significant bit. As I said, A will be most significant bit. So S0 is least significant over here, S2 will be most significant bit. So what I should connect now for SC? Yes, C I should connect to S0 because C is LSB and S0 is LSB. So B S1 and A is MSB, since A is MSB, where I should connect to S2. So this is the connection made to it is to 1 mux. Coming to input side. So these are the selection inputs, these are the outputs. So inputs. So how many inputs are there in 8 is to 1 mux? We have 8 inputs. So we name them as 0, 1, 2, 3, 4, 5, 6, 7. For 0th input, that is first input, what should be connected? D. So D is a variable. Now I have eliminated from here. This variable is treated as input to the mux. So I am connecting directly D to input 1. Then once again for input 2 is once again D. So I have shorted this, connected to input 1, input 0, input 1, I0, I1. Next I0, I1, this is I2. So I2 I should connect D bar. Where you will get this D bar? By connecting a NOT gate, you will get a complemented output here. So D is an input where you are getting this side D bar, which is connected to third input, that is I0, I1, I2. This is I2. For I0 I will be connecting D, for I1 I will be connecting D, for I2 I will be connecting D bar, complement of D. So for I3, you can see I3, I4 both are logic 0. So I will be connecting, shorting this 3 and 4 pins to logic 0. So coming to 6, once again it is connected to D. So 5 is connected to D. Okay. So now you have 1 and 1 to 6 and 7. 6 and 7 both has to be shorted and has to be connected to logic 1. So how this multiplexer will work now? So if I give this combinations, any of this combination, I should get a single output out of here. Suppose take that I am giving the input 1, 1, 0, 1. So 1, 1, 0, 1. 1, 1, 0 means 1, 1, 0 here, right? And 1 will be here. So 1, 1, 0, my output will be 1. So this particular line will be selected, that is I6. So I6 is nothing but it has got logic 1. So this logic 1 will come here. Okay. Similarly, any of these combinations, if I give over here, so the particular output from here will be directed to the output side. So this is how, this is one of the application of multiplexer. I can implement Boolean function using any of these mux, 4 is to 1, 8 is to 1, 16 is to 1. This is one of the application of the multiplexer. So next discussion over here is, suppose in a case I don't have 4 is to 1, I have got only 2 is to 1 mux. Then I want 4 is to 1 mux operation using 2:1. How to do this, right? So I think you are getting my point. Suppose we don't have, I don't have, for example, 4:1 mux IC. I've got only 2:1 mux IC with me, but I need to generate 4:1. How to do this? Available is only 2:1 mux, but I want 4:1 mux out of this. How to do? So let us discuss about how to generate 4:1 mux using 2:1 multiplexer. Fine. So I'll solve one problem here. Generating 4:1 mux using 2:1 mux. So let us design this concept using 2:1, how to get 4:1 operation. So how to design this? You can just see the block diagram I have used. 2:1 mux. How many 2:1 mux I have used here? 3. Why 3? Because at the input side I want 4 inputs. Finally my circuit should look like 4:1, but 2:1 mux has got only 2 inputs. Fine. So how to generate this? I will be using 2:1. So this appears 2 plus 2, you will get 4. But output side over here, it is single. So this single output here and here, I should get final one output. So how to design this circuit? At a time I should get a single output using 2:1 plus at the output side one more 2:1 mux. So we are going to discuss about this designing in the next session. 2:1 multiplexer, using 2:1 multiplexer to get the design of 4:1. So let us summarize what exactly we have discussed in this session. So we have started with the data processing circuit. Under the data processing circuit, so I've started with multiplexer is one of a combinational circuit. It's a data processing circuit wherein it is also called as mux. It is also called as data selector, wherein it has got many inputs and one outputs. We'll be directing out of many inputs only one output at a time, so through selection lines. So this selection lines and input lines, so there is a relationship between a selection line and input line. So this selection line and input line, as we discussed, we have the relation. So based on that we are going to decide how many selection lines we'll have. Based on the inputs we are going to decide how many selection lines we'll have, and then we are going to redirect the output. So once we design, we get an equation. So from the equation we have built a logic circuit of the mux. So we have such logic circuits built in MSI ICs. So available we have 16:1 mux, 8:1 mux. So using multiplexer we have generated 3 input function. So the Boolean function can be generated using this multiplexer IC. So I can generate 3 variable or 4 variable using 4:1 mux, 3 variable using 4:1 mux, 4 variable using 8:1 mux. Similarly, I can design using a basic 2:1 mux to the upper version like 4:1 mux by combining this 2:1 multiplexers. So let us discuss this in the next session, how to design the multiplexers using basic 2:1 mux for the higher version. Thank you.